Hi everyone. In the previous lecture, we discussed how to find zeros in MOS based amplifier using some intuitive methods. Now in this lecture, in a similar way, we will try to derive some simple intuitive conditions using which we can find poles in MOS amplifier circuits. So we'll start with the definition of a pole. So when you apply a finite input which is less than infinity, okay, at some value of s equal to sp, where sp happens to be a pole of the system, your output will become infinity. So that's the mathematical definition of a pole. So now we'll try to use this condition to find poles in a MOS amplifier circuit. So first, again, in a similar way as we discussed in the previous lecture, any MOS amplifier circuit comprising of resistors, capacitors, inductors and MOS devices can be represented from the output port. As far as the output port is concerned, it can be represented by this model, by a transconductance amplifier model, as a voltage controlled current source with an impedance Z out in parallel. Okay, so and this voltage controlled current source Gm times Vi, I'm going to call it as I out. So this I out can be measured by short circuiting the output, okay, and keeping the input alive. Vi is finite, and we will try to measure the current flowing through this short circuited output node. And Z out is measured by making input go to 0 and finding out the output impedance of this amplifier circuit. Okay, seen at the output terminal. In this Z out, we are excluding ZL here. So whatever load impedance it is connected, we are excluding that and trying to measure the output impedance seen at the output terminal of the amplifier. Okay, and for when you measure output impedance, we make Vi equal to 0. So this is something we are already aware of. So now from this model, we will try to see how to find poles. So your output voltage is simply I out times ZL parallel Z out. So from that we can directly see, if I want to find the condition under which your under which your V naught or output voltage becomes equal to infinity, that will simply be when I out is infinity or ZL parallel Z out is infinity. The total output impedance, including the load impedance, should become equal to infinity. Then we can say we have a pole at that value of S for which we satisfy either of these conditions. But we have to exercise care when we are applying these conditions. So first condition is when your output current, where I out becomes equal to infinity at some value of S. So you should ensure at the same value of S, neither ZL or Z out should become equal to 0. If either of them becomes equal to 0, then it means that there is a 0 at that value of S. So there will be a pole 0 cancellation. So we should ensure that if your I out is becoming infinity at some value, at the same value, neither ZL or Z out should become equal to 0. In a similar way, we can use the converse of this condition, so which is your ZL parallel Z out being infinity. That's obviously we saw that will be a condition for a pole. But at that value of S, your I out should not be equal to 0. Because if your I out is 0 at that value of S, then there is a pole 0 cancellation. Again, you won't have a pole at that point. Okay, so when you apply this condition, you have to ensure that this condition is met. So the second condition can be written. So this is nothing but if your ZL in parallel with Z out, we are looking at a condition where the equivalent of these two are blowing up. That will happen if your ZL equals minus Z out. So that's what, again, this is something we already discussed. So both these impedances will cancel out, if I can use that word. So they both impedances will cancel out and it will look like an infinite impedance. So this is the condition that we'll have to apply. This can also be written as YL equals minus Y out. So whichever is easier, we can apply that. So these are the two conditions. We'll apply them now to find poles and zeros in some example MOS amplifier circuits. So the first circuit is a standard or a simple common source amplifier with source degeneration, where I've made both the source degenerated impedance ZS and the load impedance ZL as frequency dependent. Now our goal is to find poles in this circuit. So first I'll state another assumption, that we are assuming in this example lambda is 0 or R naught is infinity. So which means the impedance seen, the Z out for this circuit is going to be infinity, because I'm going to look into the drain. Since your lambda is 0, there is no relationship between drain to source, okay, source terminal. So even if I wiggle, or even if I change my drain terminal by an incremental value delta V, there is going to be no current flowing in the circuit. I mean, no current flowing from drain to source. Okay, because R0 is infinity, there is absolutely no relationship between drain and source. It's fully isolated. Okay. So in that case, since Z out is infinity, so the only condition that I can think of to use to find the pole is when ZL is infinity. And ZL equals infinity happens at 2R equals minus 1 by SC. So I'll say the first pole will occur at minus 1 by 2 RC. Okay. So mind you, at this point, we are saying ZL becomes infinity, but you have to keep in mind your I out should not be equal to 0 at this value. Right? If I out is 0, then we'll have a pole 0 cancellation. So that's why if you see your I out, actually if you recall from the previous lecture, we derived the condition under which I out becomes 0 is when ZS blows to infinity, and that happens at minus 1 by 2 RC. Oh, sorry, minus 1 by RC. Okay, so this happens at a slightly higher frequency than this. It's twice the pole frequency. So we can say that I out doesn't go to 0 at the same value of S, so therefore this value of S is fine. So there is actually a pole at minus 1 by 2 RC. Had this R, instead of 2R, had it been R, then there would have been a pole 0 cancellation. Okay, that's it. Now we'll try to find, because there are two capacitors, you can have a maximum of 2 poles. So we'll see if there is other condition to find the pole. So the other condition is when I out becoming equal to infinity. So for that, what I'll do is I'll just short circuit the output and try to find I out. So we know for a MOS amplifier with a source degenerated impedance ZS, the effective transconductance is given by GM by 1 plus GM ZS. Okay, so your I out will simply be GM by 1 plus GM ZS into VI. And we have to equate this to infinity. So then that simply boils down to the condition 1 plus GM ZS is 0. So you get ZS equals minus 1 by GM. So if I satisfy this condition for some value of S, then your I out is going to be infinity. Now this is mathematics, of course. We can also see intuitively what happens at that value of ZS when ZS becomes equal to minus 1 by GM is that if you see in this circuit, if your VI, so VI is the voltage entirely appearing across this, part of it appears across VGS and part of it appears across VS. So I'll call this voltage as VS. So if I can show at some value of S, if your Vs becomes equal to infinity, then if Zs is finite at that value of S, if Zs is finite at that value of S, then I can say I out is infinity. So all I need to do is to find a voltage or value of S at which the Vs at this point becomes equal to infinity. So if you see, this looks like a simple common drain amplifier. All I'm supposed to do is find the value of Z or the impedance or the value of S for which the output voltage becomes equal to infinity. So all I can do is directly ground the input and try to find the output impedance seen at the source terminal blowing up to infinity. If I find that condition, then that may be a condition where Vs becomes equal to infinity. So all you need to do is you need to ensure at that value of S, your I out is non-zero. That's it. So I'll apply that condition here. So which is what I said is that we are trying to find out a condition under which your Vs becomes equal to infinity, and that I'm saying can be found by finding the net impedance seen at the source terminal. Okay, again I can represent this entire MOS amplifier by its Thevenin equivalent, and so I'm just finding the resistance seen at that point, okay, or by a transconductance amplifier model. So that is seen at the source terminal now, okay. So the value of Z out or the impedance seen at the source terminal completely blowing up to infinity will actually be the value where your Vs will be infinity. And if you satisfy that condition and if Zs happens to be finite there, then I out is going to be infinity. So all I need to find is the point where, or the impedance or the value of S for which the impedance seen into the source terminal blowing up to infinity. So the source terminal impedance is Zs in parallel with 1 by Gm. So that equivalent circuit is what I've shown here. Zs parallel 1 by Gm is capacitor C, resistor R and 1 by Gm in parallel. Okay. So the net impedance should blow up to infinity. That will actually happen when your 1 by SC will be equal to minus of R parallel 1 by Gm. Okay. So that's what, this condition also boils down to. We can very easily show that when Zs becomes, you will get a similar condition, Zs becoming equal to minus 1 by Gm. Okay. Or I can simply say that I'll lump all the resistors together and say 1 by SC equals minus of R parallel 1 by Gm. So using that, we can very easily show that the pole is 1 plus GMR by RC with a minus sign, of course. Okay. So this is one intuitive way of looking at it. There is other way of looking at it as well. If let's say I have slightly modified the circuit, wherein this, what I have shown here, this is a common gate amplifier circuit. Okay. So if I consider a common gate amplifier wherein I have connected a source impedance at the source terminal, okay, and I am interested in finding out, is there some frequency at which I out becomes infinity. So I can draw an equivalent circuit model for the, as far as the input is concerned. The MOS amplifier is going to offer an impedance of 1 by Gm. So now if I find the current in this loop, because the I out is simply the current drawn from the input. So if I want to find the some value of S for which the current becoming equal to infinity, that will happen when Zs becomes equal to minus 1 by Gm. So then the sum of the two impedances will be 0. So that's like the input Vi is now seeing a 0 impedance, so therefore the current drawn out will be infinity. Okay, and that happens at Zs becoming equal to minus 1 by Gm. Okay, all of this will give you the same results. Finally, the pole can be found as minus 1 plus GMR by RC. Okay, we started with directly using this condition, I out becoming equal to infinity, and we got the same result. I just gave some intuitive explanations using two different circuits. That's it. So these are the two poles. This is the second pole in the circuit, and the first pole we said was minus 1 by 2 RC. The second pole is actually, at, if I write it in more in a better way, it will be C into R parallel 1 by Gm. And if you see, at both these poles you don't have the 0. The 0 happens to be at minus 1 by RC. So this is the point where your I out becomes equal to 0. Okay, and we derived this condition using I out equal to infinity, so we don't have to worry about that condition. Okay, the condition that we are supposed to worry about is either ZL becoming equal to 0 or Z out becoming equal to 0 at this value. And that doesn't happen because you can see ZL will become 0 at only infinite values because it's just a capacitor. The capacitor will become, impedance of the capacitor will become 0 at infinite frequencies. So we can use this condition. So these two are real poles. Now this circuit is again the similar circuit we discussed in the previous lecture. So wherein we have a capacitor between gate and source terminal, and we are supposed to find poles for this circuit. So first I'll see if there is any condition. The first condition is using I out equal to infinity. If I out is infinity, the expression for I out for this will simply be Vi into Gm plus Sc. So that's the current, the sum of the two currents, which will be Gm Vi plus Vi into Sc. Now if I want to equate that to infinity, that happens only at infinite frequencies. That can be intuitively seen here. At infinite frequencies, capacitor will behave like a short circuit. So from the input there is a direct short circuit to the output, and so the current drawn will become infinity. Okay, the current flowing through the capacitor will be infinity at infinite frequency. Therefore, I out will also be infinity. Okay, so there is no finite pole. Using this condition, we didn't get a finite pole. The other condition is ZL parallel Z out becoming equal to infinity. So the net impedance seen at the source terminal becoming equal to infinity. So that is simply, I can define the overall impedance seen at the source terminal will simply be 1 by Gm in parallel with RL in parallel with the capacitor C. Right now I've ignored R0 here. I mean, even if you assume R0, that's going to come in parallel with this. So you'll have an extra R0 in parallel with this. So using that, I can simply say the total capacitive impedance 1 by SC, if it's equal to minus of the resistive impedance, minus RL parallel 1 by GM, we are going to get the location of the pole. So that's where the impedance is going to blow up to infinity. So that happens to be at minus 1 plus GM RL by RL into C. So that is, I mean, we can simply leave it in this term. So it will be minus 1 by C into RL parallel 1 by GM. So if there is R0, you will also get R0 in parallel with this. So if you see here, this is the value of pole, and we derived the expression for 0 in the previous lecture. That happens to be at minus GM by C. Okay, so your current doesn't go to 0 at that point. So this is actually a real pole. The next circuit here, we are supposed to find poles for this circuit. So I mean, again, I'm just considering only capacitors which are shown here. I'm ignoring all the device parasitics in these examples. Okay, so because we'll take it for simpler cases and solve it first, then we'll complicate it at a later stage. So we are supposed to find a pole for this circuit. If you see your short circuit output current, when I short circuit it, your output current is simply going to be the MOS current plus the current through the resistor, and there is no frequency dependence there. So it's never going to blow up to infinity at any value of S. So we can't use the first condition. The second condition is the total impedance seen at the output node, ZL parallel Zout, should become equal to infinity. So that will simply reduce to, I'm grounding the input, and the impedance seen here will simply be resistor R0 in parallel with the capacitor CL. So that will blow up to infinity when 1 by SCL becomes equal to minus R0, or the pole will happen at minus 1 by R0 CL. We said I out is completely independent of frequency here. So therefore it will never go to 0 at that value. I mean, I haven't explicitly written what I out is here, but you can very easily show it yourself. Your I out will actually be equal to GM plus 1 by R0 into VI. So this is the simple common source amplifier. We have a load capacitance CL and RL, and I mean, here I've assumed lambda is not equal to 0, so there is also finite R0, and you're supposed to find the pole. Again, if you want to find the short circuit current I out, it will simply be minus GMVI in this case, and since it is independent of value of S or frequency here, it's never going to blow up to infinity at any value. So we have to use the second condition. So the total impedance seen at the output node, ZL parallel Zout, should be equal to infinity. Using that, we can directly show the pole will simply be 1 by SCL should be equal to minus of RL parallel R0. So if you use that condition, you will get the pole. So and that value, obviously your I out is not going to go to 0 because it's independent of frequency. So finally, I wanted to take one example to show where, we might violate some conditions. So meaning we might encounter some special cases when Zout is infinity but I out happens to be 0 at that point. So I wanted to take one example to show you that condition as well. So here in this problem, it's given you're supposed to ignore R0. So R0 is infinity or lambda is 0. Okay, and you're supposed to find poles in the circuit. So the first condition I'm going to use is that, so I mean, we can also use I out equal to infinity, but I'll try to use the condition first, the condition Zout being equal to infinity. So that is the total impedance seen at the output node you're supposed to find. Here ZL is infinity anyways to begin with, so it's open. Okay, so you're supposed to use the second condition, so which is ZL parallel Zout. So since ZL is infinity, so we are just going to use this condition ZL equal to infinity to find the pole. So that is simply the output impedance of this amplifier. So that will simply be a capacitor C in parallel with 1 by GM. So if you want to find the pole for this, you'll just have to use this condition 1 by SC, the impedance of it should be equal to minus GM. So there is a 0 at minus GM by SC. So the question is this actually a 0 for the circuit? there is a pole for the circuit. Sorry, this is SP. Pole happens to be at minus GM by SC. The question is this actually a pole for the circuit? So we already derived in the previous lecture, if you try to find I out for the circuit, that happens to be GM plus SC into VI. And I out goes to 0 at SZ equals minus GM by C. So therefore, even though we calculated the value of pole to be at minus GM by C, at that value your I out also goes to 0. So therefore, this is not a real pole. Okay, so the pole and 0 will cancel out, so you won't have a pole at GM by C in the circuit. Okay, so that's it. So that's it about finding poles for, and we have also discussed zeros in the previous lecture for simple MOS amplifier circuits using some very simple intuitive conditions. In the next lecture, I'll start with the discussion of single stage MOS amplifiers, the frequency response of single stage MOS amplifiers.